Hi, Assalamualaikum, and have a good day. This is controller design in a frequency domain topic. So for today, we cover on frequency response technique lecture based on review on board diagram plot and relative stability. So there are 4 learning outcomes: to explain the concept of frequency response, able to plot the open loop board diagram. The next one is to analyze system performance based on the board diagram, and the last one is to design desired system response through cascade compensation through lead, lag, and lead lag compensation. So this is dynamic signal analyzer to obtain the frequency response data from physical system using sine wave to measure the relationship between input and output of the system. So frequency response representing the magnitude response. Phase response in frequency domain we label as omega. The unit is radian per second. So magnitude response is the ratio of output signal magnitude to the input signal magnitude, y over x. And the phase response is difference in phase angle between the output and input signal. So the advantage of frequency response is when we model the transfer function, when we design lead compensator and also lag compensator for fulfill the steady state error requirement and also the transient response requirement to find the stability of the nonlinear system. So board plot in magnitude plot, the unit is decibel, so versus the frequency omega in radian per second, while for phase the unit is degree versus frequency omega in radian per second. So for this one, we will refer to the next lecture, notes on 10 frequency response theory. So there are 4 steps in sketching the board plot. The first one is we determine the open loop transfer function of the system. This one usually in S domain. The next one, we need to rewrite this open loop transfer function in proper form where we replace S with J omega. And then the next one, based on this transfer function in frequency domain, we construct an approximation table. We call it as board table, indicating the magnitude and phase frequency plot for each factor. This one should be based on 10 frequency response theory. And based on this board table, we need to draw the overall magnitude and phase plot for the systems. And based on this phase and magnitude plot, we can determine the stability of the system. So to determine the stability, it's based on gain margin. And also the other one is phase margin. Okay, to determine the gain margin first, we refer to the negative 180. This one is actually negative 180 from the phase plot. So this is your omega PCO, phase crossover frequency. In this case, it labeled as omega phi m. And then at this value, this one, at negative 180 degree, this one is omega phase crossover frequency, omega PCO. In this case, it labels as omega GM, goes to the magnitude plot, and then this gain will be read as this one, the gain at omega PCO. So use this formula to determine the gain margin. And the next one, for phase margin, we refer to 0 dB of magnitude plot. This one, at this point, the frequency we read as gain crossover frequency, or this case labeled as omega phi m. So at 0 dB, go to the phase plot, and then we read this location of phase and represent as phi m, and then we use this formula to determine the phase margin of the system. Besides the question that you need to plot the frequency response board plot from the transfer function, the other way around is obtain the transfer function from board plot. The question will give you a board plot, and then you need to determine the transfer function of the system based on 3 characteristics: the system type, based on the slope, initial slope, and then check the difference between the number of poles and number of zero. And the second one is based on slopes. So this magnitude and phase curve represent first order or second order pole or zero in the frequency response plot. And the last one is break frequency to determine pole and zero from the transfer function that estimate the break frequency. So that's all for frequency response technique. See you in the next lecture. Thank you.